Let's now discuss how calculators work, basically, for calculating e to the x and natural log x. For e to the x, basically, the calculator, or at least a lot of implementation of a calculator, will basically change a number to its binary representation. So, for example, suppose we have e to the, I'll just pick a number out of the hat, the 27.6. The calculator will then write this as e to the 27 times e to the 0.6. Now, e to the 27 can be figured out using the law of exponents and certain predetermined values. So, for example, this can be written as e to the 16th times e to the 8th times e to the 2nd times e to the 1st. So that would be 24 plus 2, 26, 27. The significance of 16, 8, 2, and 1 is that those are powers of 2, and 27 base 10 is equal to 1, 1, 0, 1, 1 when written in binary, base 2. So the calculator can store certain values ahead of time. So rather than recompute these things every single time, e to the 27th can be found by multiplying a few certain numbers that are stored in memory. Now how about e to the 0.6? E to the 0.6 can be found by Taylor series. So that's equal to the sum from n equals 0 to infinity of 0.6 to the n divided by n factorial. Now the terms in this sum will die very quickly. The number on top is less than 1, so the numerator is decreasing. Furthermore, the denominator is decreasing very, very rapidly. So after, in this case, certainly about 8 terms or so, this will be the terms in this series will be significantly smaller than the accuracy of the calculator. So the calculator does not evaluate this to infinity, but it does evaluate it to enough terms so that there's no change as far as the calculator is concerned because of the floating point accuracy of the calculator. So that is a brief discussion of how a calculator can be programmed to calculate e to any power. The integer part can be found by just simply multiplying a few values that have already been stored in memory, while the decimal part, in this case e to the 0.6, can be found by Taylor series. The computation of the logarithm of x proceeds in a similar manner. So suppose a problem is the natural log of, and to pick a number out of the hat, 24,680. Then this can be written as the natural log of 10,000 and let's make that 100,000 times 0.2468. And I chose 100,000 to make sure that the second part is less than 1. So this is equal to the natural log of 100,000, which is 5 times the natural log of 10, plus the natural log of 0.2468. Okay, so the natural log of 10 can be stored in memory of the calculator, and then that number just needs to be multiplied by 5. So that's the first part. Now to get the second part, where I have the natural log of a number that's less than 1, the easiest thing to do again is to use Taylor series. Now the Taylor series in mind is actually going to be something a little bit different than the normal Taylor series expansion that you hopefully saw in calculus. That natural log of 1 plus z is equal to z plus z squared over 2 plus z to the third over 3. I'm going to go out to 5 terms, z to the fourth over 4, z to the fifth over 5, and so on. We're going to use a slightly different series to actually get less terms. 1 minus z, if I take the natural log of 1 minus z, if I replace z by negative z, then I would have negative z, then plus z squared over 2, then minus z to the third over 3, then plus z to the fourth over 4, and the signs alternate, finally minus z to the fifth over 5. And both of these series are correct if the absolute value of z is less than 1. So if I subtract the two, so natural log of 1 plus z minus the natural log of 1 minus z, if I subtract these two lines, then the even powers go away. Z squared over 2 minus z squared over 2, that goes away. Same here, z to the fourth over 4 minus z to the fourth over 4 goes away. The odd powers, however, stay. So z minus negative z is 2z. Then the next bit, z cubed over 3 minus negative z cubed over 3. The double minus makes a plus, so 2z cubed over 3. And then 2z to the fifth over 5. And so on. And the left-hand side, natural log of 1 plus z minus natural log of 1 minus z, just by the laws of logarithms, is equal to the natural log of 1 plus z over 1 minus z. And the advantage to this expression is that the terms are being multiplied by z squared, and the denominators are decreasing a little bit faster. So this bottom series converges quicker than either of the top two series. So all this to say, to get the natural log of 0.2468, what needs to be done is to find the value of z so that 1 plus z over 1 minus z is equal to 0.2468. So solve for z. Once that value of z is known, then we plug into the right-hand side, and we take enough terms to evaluate the second part of the expression up here. So 5 natural log 10, that's knowable from just simply calculating the natural log of 10 once and storing that in memory, while the natural log of 0.2468 is found by Taylor series, typically the second Taylor expansion, or the bottom Taylor expansion that's seen on the screen right now. We set 1 plus z over 1 minus z, and in this case we set that equal to 0.2468. We solve for z, and then we plug into the right-hand side.